Hello friends, welcome to part 3 of physics paper solution. This is mechanics, this is the paper C2, and in part 1 and 2 I have solved up to question number 4C. In 4C there were two questions, either solve this one or this one. I have solved the first one in the part 2. Now I'm going to solve from the next part of question number 4C. So this paper is said by Dibrugarh University first sem, for the first sem, BSc first sem. So let's start the video. Before you start, please subscribe the channel if you are new to my channel, and share with your friends. And if you like my videos, then hit the thumbs up button. Also hit the bell icon so that you get notified when I will upload new video. Okay, so let's start. So this is question number 4. Here you can see or there was another part which was already solved in part 2. So I will provide the link of part 2 in the description box. Okay, so here you see, state Kepler's 3 laws of planetary motion. Prove any one of the Kepler's law. First, let me write the statements of the 3 laws of planetary motion, and those are Kepler's planetary motions. So here is the first law. It states that each planet revolves around the sun in elliptical orbit with sun at any one of the foci, any one of the two foci, right? That means a planet, this is the sun suppose, and a planet revolves around the sun, this is the planet revolves around the sun in an elliptical orbit, and this orbit, we know that ellipse has two foci, and this sun must be located at one foci. That is the statement of first law, right? So now second law states that the aerial velocity of the radius vector of planet relative to the sun is constant, right? So now you see, suppose this is the radius vector r. So rate of change of so area swept by this radius vector is suppose a dA in time dt, then this dA by dt is constant. This is the second law, statement of the second law. Now you see, third law states that the square of the period of revolutions. That means if the planet completes one revolution in time t, capital T, then this is going to be proportional to the cube of the semi-major axis, of the ellipse. So we know an ellipse, suppose, so let me clean this one. So this is the elliptical orbit. So an ellipse has two axes. This one is called major axis, and this one is called minor axis. And semi-major axis means length of this one. This is suppose A. If the semi-major axis is suppose A, then the time of revolution, the time period of revolution, this planet suppose P takes time capital T to complete one revolution, then square of this must be proportional to cube of the semi-major axis, right? So this is the third law. So now let me prove the second law. Okay, so here in the question it is given that prove any one of the Kepler's law. So now let me go to the next slide. Okay, so let us prove the second law. So here you see, let us consider that S be the sun of capital M, mass capital M, and a planet of mass small m. Okay, a planet of mass small m, and this is sun, this is the planet P with position vector r, and this is small m, and it revolves, and after a time interval it reaches to suppose q, right? And its position vector at this point is suppose r vector plus del r. Let me consider that way, right? So that displacement is del r, and let me complete this parallelogram. Okay, so let me draw this PQRS be a parallelogram, right? So now you see, in this case, this planet is revolving around the sun in the elliptical orbit, which is at one of the foci of the two foci of this ellipse. The force acting between the planet and the sun, the gravitational force, is given by F is equal to this minus capital G capital M small m by r square. So r cap, right? So r being the position vector, relative to sun. Hope you know that. Then now you see this r cap represents the unit vector of r vector, right? Unit vector of vector r. So this is r square capital G capital M small m by r square, right? So r cap will be given by vector r by magnitude of vector r. So vector r by r, that means. So if you use this relation here in this equation, then here you will get r cube, and this is vector r. So minus capital G capital M small m by r cube vector r. So we can consider this part. You see, you can consider this part as a function of r, f of r as a function of r, and this vector r is this one. This is the vector r, right? So function of r, f of r, this is a scalar function of r. So the torque acting on the planet will be given by this torque tau is given by vector r, position vector r, into the force, cross product of the position vector and the force acting on it. That force is given by from this relation. You see, from this relation that here we have got force F vector. From this relation we have got this one, capital G capital M small m by r cube, and this is vector r. So which is equal to function of r into vector r, right? You have got this relation. This is what we have got, f of r. This is a function of r and with r vector. Now if you use this equation here, here you can see this is vector r cross vector f, right? If you use this vector f here, this here you see this is nothing but, this one is, let me write it properly, this one is nothing but f of r into r vector. So if you use this here, so you will get f of r vector cross r vector, right? So r vector cross r vector will be equal to 0, right? So that's why the torque acting on it is equal to 0. The torque acting on it is equal to 0. So in books what happens, actually they, instead of writing the vector symbol, they used to write the letter representing vector bold. Okay, so where you have bold letters, you must know that there is a vector quantity, right? So as the torque acting on the planet is 0, the angular momentum of this planet relative to the sun is conserved. That means you can consider that here you see. So let me clean this part. Now you see one more thing, that here we have got torque is equal to 0, right? Torque is equal to 0, and we know that torque is nothing but rate of change of angular momentum. If its derivative with respect to time, if the derivative of L, that is angular momentum, with respect to time is 0, then this L, that is angular momentum, must be constant. It must be constant, right? So here we have got this angular momentum. Here they are using the letter J, capital J. This R cross P is equal to R cross M V. So vector V, this is R vector, right? So this is constant. So instead of L, they are using J actually. So let me write here J. So from this relation, what we have got from this relation, so torque is 0, and torque is nothing but rate of change of angular momentum is equal to 0. That's why this angular momentum J must be constant, right? That must be constant. Now you see, if you see this, Now let us consider that P be the instantaneous position of a planet. We have considered this PV, the position of a planet at an instant relative to the sun, and the position vector of P relative to the sun is given by R vector. So after time del t, the planet is at Q, having position vector R vector plus del R vector, right? R vector plus del R vector. Let me write here clearly. R vector plus del R vector, such that here you see then the displacement del R is nothing but here PQ vector. This is PQ. So displacement from P to Q, this one. So displacement from P to Q, if you see the diagram here, displacement from P to Q, this is the del R vector. So now the area swept out by the radius vector SP, this is the SP, right? Area swept by it in time del t is given by del A. So let it be del A, area of the triangle PQS. So area of this triangle PQS, right? Now you see how to find that area of this triangle. So now you see, in order to find the area of this triangle, PQS, so let me complete, I have completed this parallelogram PQRS, okay, PQRS, this is PQRS. I have completed this parallelogram because diagonal of a parallelogram divides it into two triangles of equal areas. So if we able to find the area of this parallelogram, if you take half, then you will get the area of this triangle. So now you see what happens actually. Suppose you have taken a parallelogram and you can consider that these sides represents two vectors A and B, right? Then their cross product will give you the area of this parallelogram. Okay, so let me tell you how. So this is a concept of vector. Hope you know that. If you see, suppose this is your parallelogram, right? This one side is vector A, another side is vector B, right? An angle between them is theta. We know area of a parallelogram is given by the base into base into height. So here base is suppose A. Here if the vector A is this side, then its length will be given by the magnitude of this vector, that is A, and this height, if you use trigonometry, this will be given by B sin theta, right? B sin theta. So AB sin theta. So area will be AB sin theta. So length into height. So AB sin theta means it gives A cross B, right? It is A cross B. So similarly, here you see this vector is R vector. This vector is R vector, position vector R vector, and the displacement vector is del R vector. So the area of this parallelogram will be given by cross product of R vector and del R vector. So let's move on to next slide. So here you can see the area of this parallelogram, area of the parallelogram PQRS, right? That is vector R cross vector del R, right? So area swept by the radius vector per second is given by so if you consider this area as dA, so dA by dt, so aerial velocity will be dA by dt. So that can be given by the limit of del A by del t, you can see here clearly, del A by del t, right? So del t tends to 0. So that means we have considered these P and Q are very small. They are very close to each other. Okay, this area is very small area. T tends to 0. In very small time, the area swept by the radius vector will be very small, right? So we have considered that way. So del A is given by half R vector cross del R vector, right? So it can be written as, so half of R vector is taken outside of the limit, then limit of del R by del t will be given by dr by dt, right? Dr by dt. So that's equal to half. we know dr by dt is nothing but velocity, right? Velocity, right? So hope you have understood this. Just wait, cut this one. So now you see, as you can see that r cross b, right? So we have already got that we have already shown that this angular momentum z vector is constant. We have already shown that constant, and we know angular momentum z is equal to that r cross mv vector. This is angular momentum, right? So here it can be written as r cross vector v by j by m. We know that here we have already shown that angular momentum is constant in this motion, planetary motion. So if j is constant, and we know mass is also constant, so that's why as a whole this is constant, right? So j by m is constant. So here you see, here in this equation r cross v, this can be replaced by j by m. So dA by dt, that aerial velocity is given by half j into m, which is also constant. So the Kepler's second law is proved. So hope you have understood this. Now let's move on to next. So here is the question number 5, as you can see. So find out the expression for the potential energy. W is equal to 1 by c phi square of twisted cylinder when it has a twist of phi. This is phi, okay, twist of phi. So now you see, so here what we have done, so we have considered a cylinder as shown in this figure, that cylinder, and is twisted, and let AB be the line parallel to the axis of the cylinder displaced to AB dash, right? Here you can see this black color is AB. So here, that means if you can see the diagram clearly, this one is AB, right? This one is AB, and it is twisted and displaced to AB dash. This is B dash, right? And here you see an angle between them, AB and AB dash, is theta. Angle between them, AB and AB dash, is theta. So this is theta, right? And this AB is parallel to the axis O dash. This is O dash, right? O dash. And angle subtended by the arc B dash at the center is phi. This angle is phi, right? This angle is phi. We have considered that way, right? So now imagine that cylinder is cut along AB and flattened then before twisting occurs. So we have got ABCD rectangle, right? And should be formed, this ABCD rectangle should be formed before deformation, before it is twisted, but after twisting it becomes AB dash C dash D, right? After twisting we have got this. So angle between AB and AB dash, that's is theta, right? Here you can see. So I have imagined this is a cylinder and it is cut along its axis along AB, so and flattened to give this rectangle before it is twisted. So rectangle is supposed to be ABCD, but after twisting it we have got AB dash C dash, right? That means CB is displaced to C dash B, right? So hope you have understood this. Now let's move on to next slide. Here you can see So this is a cylinder, a cylindrical cell. Just wait. So let me also imagine this is the cylindrical cell. Through theta, right? So I have assumed this cylindrical cell. Here you can see through theta, right? So now you see, referring the figure A, we have from triangle B O dash B dash. So this is B dash, this is O. This is the triangle B O B dash, B O B dash. And here you see the arc. Here the length of the arc BB dash will be angle into the radius. So angle is phi cross O dash B, right? Cross O dash B is the radius. So if you see, this is B dash, and this is the O dash, and the radius is, this is the radius O dash B, and phi is the angle between this, and I have considered O dash B is x. Let me consider it that way. Then again, for the arc from the triangle BAB dash, right? This is this triangle. You can see BAB dash, this one. So here you will get the same arc, length of the same arc, theta. Here we have taken the angle between AB and AB dash is theta. So that's why theta into AB, that is, we have considered the length AB as L, right? AB as L. So L theta we have got. So both are representing same arc. So we can write L theta is equal to x phi, right? So theta will be equal to x phi by L, x phi by L. So theta is equal to, we have got x phi divided by L, right? So now you see, let F be the tangential force acting on the base of the elementary cylindrical cell considered. We have considered a elementary cylindrical cell that I have already shown in the first slide. We have assumed a cylindrical cell through the angle theta, through this angle theta, right? Between the AB and A dash B, sorry, AB dash. So since the face area of this cell, so that cell I have taken, this was the cell, and this was the cell we have assumed, right? Here is A, sorry, not A, this point is A, B dash, we have assumed that way. So this theta, through this theta. Now you see, we have considered this thickness. This thickness is, suppose, dx, right? Then area of this ring will be given by 2 pi dx, right? Because this is very small. If you consider you have vertically cut it, then you will get this one, this ring, as almost as a rectangle. Okay, it will take the shape of rectangle, but not exactly rectangle, just similar to rectangle. So we can consider it is a rectangle. So dx is the breadth here, and length will be equal to 2 pi x, right? So if you take that r is radius, okay, r is radius of this cell. So then what we will get, the shearing stress will be given by force per area, right? So shearing stress, because this cell, you see, we have given a force to the base of this cell, and the area of this ring at the base is 2 pi x dx, and the force is applied F, right? So this is the force per area which gives the stress. So now sharing stress, hence this eta sharing stress by sharing strain, sharing stress by sharing strain will be given by F by 2 pi x dx is by divided by F by 2 pi x dx by theta. And if you put the value of theta from this equation number 1, so we have taken this as equation number 1, this equation, this one as equation number 1. If you take that one as equation number 1, this is equation number 1. What was that? X pi by L, right? So if you put that here and simplify, then you will get this result, right? So now simplifying this, we will get F is equal to 2 pi eta phi by L into x squared dx. We're gonna get this, right? So now let's move on to next slide. So this is the force we have got. Then the moment of force about the axis OO dash, that means this is the cylinder. So about the axis of the cylinder is suppose OO dash, as we have considered. So about this axis, the moment of force will be given. So moment of force, distance, force into distance here, F into x. X is the distance from the axis OO dash to the cell. That means you can consider that we have considered the radius of the cell as x. You can take that x. So now you see, if you put the value of F from equation number 2, then you will get this expression. So finally it will be x into x square, that will be x cube. So here you see, this is the couple required to twist the elementary cell of radius x through an angle phi, right? Through an angle phi. So therefore twisting couple, this torque you can consider tau. So twisting couple tau required to twist the whole rod. So here you see, this is the actually we have considered cylinder. Instead of writing the rod, write here solid cylinder. Okay, so that is written in bracket. So here you see, this is the cylinder and we have assumed the cell inside it like this, right? And radius of the cell is x, we have considered. So to get the torque, to get the twisting, twisting couple, required twisting couple to twist this whole cylinder. So we have to integrate this expression. Right? This is required to twist the cell only, tau s you can consider. We have to integrate it from 0 to radius r, right? If you consider the radius of the cylinder is r, so integrating that, we have got this twisting couple, that integrating from 0 to r. So if you integrate this x cube will be x to the power 4 by 4, and if you put the upper and lower limits, and then you will get this, right? And now you see, now here you can see this expression tau is equal to pi, this tau is equal to pi eta phi by 2l into r to the power 4. It can be rearranged in this way, that tau pi eta r to the power 4 by 2l into phi. This way you can assume that. Now you see, this is C, this is C, this part is written as C. That's why we have got tau is equal to C phi. So what is C here? C is nothing but tau by phi, and which is the couple required to produce a twist of 1 radian, right? So that is the, or you can say, restoring couple per unit radian of twist of a solid cylinder, that is given by C, right? So now you see, now work done for twisting the cylinder through a very small angle, suppose d phi is given by dw is equal to tau d phi. So tau is c into phi, c dot phi, you can consider that way, right? So tau we have already got, this one tau is equal to c phi, so we have put here c phi instead of tau, right? So here you see, if you integrate this dw, then you will get the total work done, right? Total work done. So we know dw is equal to c phi d phi, and we must integrate it from 0 to angle phi, right? And doing so, we have got half c phi square, and this is the potential energy, right? This is the potential energy. This is the work this work is stored in the cylinder as the elastic potential energy, right? So hope you have understood this. So this is the answer to this question, question number, let me show you. Yeah, question number 5a. Now let's move on to next question. Now, what is damp vibration and what will happen? Damping is large if the damping is critical, if the damping is small. So let me give you the answer. So here you see, if a vibration, damp vibration is the vibration in which the amplitude of vibration decreases continuously with time, that is called damp vibration. And if the damping is very large, the mass do not even oscillate, and when displaced, it attempts to come to the equilibrium position, right? And what if it is critical, damping is critical, then system returns to equilibrium as fast as possible. And third question, damping is very small, then vibration remains approximately periodic. Its amplitude decreases slowly, right? So this is our next question. So what is forced vibration? So that means same question, there were two questions. First one is this one, either you should solve this one or you have to answer this one. So what is forced vibration? Discuss the condition for resonance in forced vibration. So this is the definition of forced vibration. Here you can see that the vibrations of such a body die out with time due to dissipation of energy. If some external periodic force is constantly applied on the body to continue its vibration or oscillation under the influence of such external forces, such vibrations of the body are called forced vibration. Okay, so equation of the forced vibration is given by this equation. This is suppose equation number 1, and here P is the angular frequency of the applied periodic force. We have assumed that way. So now you see, this mu represents the coefficient of friction. This mu is the coefficient of friction. And the K is the restoring force per unit displacement. Okay, so this K represents force per unit displacement, right? Now let's move on to the next slide. here you see, and solution of this, if you solve this equation and if you solve it for y, so you will get the displacement. Then the displacement is given by this, so this is the solution of that equation number 1. So how to solve this one, that is not required here, that is not our concern. So here you see, in effect of viscosity of the medium, instead of writing that, you can write friction. Okay, friction due to the medium. The amplitude is given by this, and now you see, under the action of driving force, that means the force which continues the vibration or oscillation, is maximum when this denominator is minimum, right? So that's why this condition is possible when if k minus mp square is equal to 0, which gives k is equal to mp square. So therefore from this equation we will get p is equal to this, right? And to get the resonance, the vibration of the system will be called resonance. If you see, the oscillation will have maximum amplitude in this condition only. That means when the force frequency is equal to the natural frequency of vibration of the body, then you will get the resonance. Okay, so now what will be the amplitude? Now if the friction is present, then amplitude at resonance, so let me write here, is given by f by mu into root over mk, right? So basically this is the condition for resonance actually. Right, so hope you have understood this. So if you have understood, share this video with your friends and hit the thumbs up button. And if you are new to my channel, just subscribe the channel and also hit the bell icon so that you get notified when I upload new videos. And remaining questions will be solved in the next 2 parts. Okay, those will be coming soon, part 4 and part 5, I think. Okay, so I have to make, I think, at least 2 videos for the next questions, the remaining questions. So thank you for watching. See you in the next video.